Great. Thanks a lot, Sonia. Can you hear me okay? Wonderful. All right. Welcome back, everybody. Wonderful to see you. And we're going to be jumping right in tonight into our topic of large language models. We've got a couple of experts, people who've really devoted the last number of years into working in this domain area. So very happy to have them here. But to set us up, I've asked my colleague, Graham Taylor, who's professor at University of Guelph. Many of you have met Graham already at the reading group. And also he heads research at the Vector Institute. And Graham, if you don't mind just kicking us off, first off, thank you for being here tonight. Just to set the scene for people for whom this is not their area of expertise, of what is distinct about large language models relative to the kind of general, let's call it machine learning or deep learning in particular, that many people might be a little more familiar with. What's special about these models? And then we'll introduce Jimmy.
Thanks, Ajay, for the opportunity to talk to this group tonight. So in one of the readings that we assigned for tonight, this is the Bomasani and colleagues paper, they call these large models like BERT and DALI and the GPTs foundation models. And fundamentally, these models are based on two ingredients. They're trained on broad data using self-supervision at scale, and they're adapted to a wide variety of tasks. And so-called pre-training, the first step, and then fine-tuning the second step, those really go back to the early days of deep learning when I was a grad student. So why are these models worthy of a new moniker? So the authors say, and I quote them, these models are based on standard deep learning and transfer learning. It's their scale that results in new emergent capabilities, and their effectiveness across so many tasks incentivizes homogenization. So in emergent capabilities and homogenization, they're pretty technical terms. So I'm just going to take a moment to dig into both of those. And I'm going to do this through the evolution from machine learning to deep learning to foundation models. So as you've learned either before this group or through this group, deep learning is a type of machine learning, and foundation models are a type of deep learning. And as on a historical note, the branding deep learning came about a half century after the first use of machine learning, and the term foundation model came about a decade after the use of deep learning. So things are speeding up. And with the introduction of machine learning, how a task is performed emerges. So more specifically, it's inferred automatically from data rather than being explicitly programmed by a human. And as many of you know, in deep learning, the features to do that task emerge from the data. And then with foundation models, advanced function like in-context learning emerges. And in-context learning, you're going to hear more about it today, but this is this idea to adapt a model simply by prompting it with some new text, not really explicitly training it or even anticipating the need for the knowledge about that task, that task is even going to be asked of the model. So that's emergence. And then homogenization, the second key thing here is that machine learning homogenizes learning algorithms. So, take optimizing a loss by gradient descent. So many models are trained that way. And deep learning homogenizes model architectures. So RNNs and convolutional nets and transformers, those are all examples of that. But foundation models homogenize the model itself. And the example here is a model like ChatGPT. I interviewed 77 startups 2 weeks ago for Next AI, and the fraction of them that are building applications on top of ChatGPT is just indicative of this level of homogenization of a single model. So that's why they're a big deal, and that's why we're talking about them tonight.
Excellent. Thank you, Graham. And I just ask, one of the reasons that we started the reading group, it was deep in the early days of the pandemic, was to keep together the CDL community when we were dispersed and couldn't meet in person. And so if for those that have joined for the first time, and if you don't mind turning on your cameras if you can, if you're able to turn on your cameras, because that way we can sort of see everybody, and it just helps a little bit with the community development. So please, if you can, turn on your camera. Okay, so as we were thinking about how we would tackle the subject of large learning models, we thought through who would be great to talk about this subject area. And the first up is Jimmy Bob. And Graham, if you don't mind introducing Jimmy for the group.
Sure. So Jimmy is a colleague at the Vector Institute, where he's a faculty member and he holds a Canada CFAR AI chair. He's an assistant professor in the Department of Computer Science at the University of Toronto. And among his many accomplishments, Jimmy developed the Atom Optimizer, one of the go-to algorithms to train deep neural nets. Jimmy completed his undergraduate, his master's, and his PhD at the University of Toronto. And he studied under Jeff Hinton, Brendan Fry, and Russ Salakutnov, who some of you might know from the CDL community. And Jimmy's long-term research goal is to address a computational question on building general problem-solving machines with human-like efficiency and adaptability. In particular, his research interests focus on the development of efficient learning algorithms for deep neural nets. And he's been reorienting his research programs towards LLMs, and a key player in Vector's own LLM capabilities. I thought he'd be an optimal guest tonight for the session.
That's awesome. Thanks very much, Graham. Jimmy, nice to see you. Welcome. And so we turn over to you. Just you can offer, some introductory comments and presentation, and then we're going to open up for discussion.
Great. Yeah. Thanks, Ajay. Thanks, Graham, for a very flattering introduction. So Graham reached out to me for this CDL reading group about 4 weeks ago. And back in the days, when you run a deep learning reading group, you send out 10 invitations, maybe 5 people shows up. So I didn't quite anticipate this large turnout. Yeah, I guess let me quickly share my screen. I was told I'm supposed to, I guess, give you a 10-minute introduction of what this whole fuzz and buzz is all about, and we'll, I guess, do the reading group thing and make it more informal and see what kind of ideas we can vibe with. So I guess just follow up what Graham talked about. There's all those different confusing terminologies. This is just literally, as Graham was talking about, I was giving this lecture this week at U of T, and I just took one of the lecture slides defining different terminologies on what large language models, pre-trained language models, and foundation models are all about. So if all those concepts just go over your head, don't worry. Half of my students don't even understand what they mean, and they're fourth-year computer science students. Okay, so let's actually go to the slides I'm going to talk about today. So large language models, right? So a lot of you recently has seen the hypes and hopes and dreams of ChatGPTs and how the new Microsoft Paperclip, which is going to take over all the productivity tools. So back in the days, I think that the actual technology that behind those ChatGPT has been available to a lot of researchers, and we've been playing around with it for almost half a year now. It has been available as much as I think late 2021. So what can those models do, right? So over the course of 1 year, they actually do very well in terms of writing poem. For example, you can ask, hey, for the introduction to deep learning course I'm teaching this term, why don't you just write a parody of Lord's Prayer, right? It's pretty nice. And you can ask those models, be like, hey, can you draw me a painting of Jesus play with an iPad? And it's not perfect, especially those models. If you've been lurking around different online forums, you know that those image generation models are not particularly good at generating hands. So beyond the images and just writing poems, those models have become pretty serious contenders in terms of helping us to build tools in computers through translating natural languages to programming languages. So that's pretty fascinating. And a lot of those tools, once you train with enough of data, can actually compete with human programmers in a lot of code competition problems. So what's common among all those models, right? Like the model can write poems, the model can write code, and model can, integrate with some image generation and essentially with Microsoft Paint and paint you some interesting pictures. One is they are trained on the entire internet of text data. And two, in the backend, they're pretty much just one single model that empowers all those applications. So what does training on the entire internet of text data even mean here? So what it means is like they back in the days in machine learning, I guess back in the days of Graham and I when we were in grad school, the machine learning is all about like go out, you have some nice research ideas, and then you look around and be like, oh, someone else collected this data set with 1,000 images. Let me apply my nice ideas to those problems that people collect the data for, and you start making progress, right? And it's almost like race to the bottom. You want to be the next person who can get a higher accuracy on those 1,000 images. But these days, it's all about the machine learning. Well, at least in those cutting edge labs, is all about who can go out and collect as much data as possible and build the next generation of systems. It's less about developing algorithms on a preconceived benchmarks, but rather go out and actually collect data and define your own evaluation suites. So once you actually train on entire internet data, something magical happen. That is, you can almost think about the big deal of those language models is that it redefines what programming language is. Like back in the days, you had to learn C++ or Python to actually program a computer. But now the latest programming language is actually English. You can actually just write a plain natural language to tell and ask computer what you want to do. And it's almost like it takes a little bit of work of art to figure out how do you actually talk to this almost like a magic black box that kind of speaks English, but sometimes doesn't quite get what you mean. And so you have to tweak your words a little bit. So for example, right? So how can I use English to program a machine that can solve some very simple, counting problems we all encounter in elementary school or middle school, right? Counting the tennis balls and counting the apples. Well, what you do is that you can show examples to the machine, be like with the actual natural language, be like, hey, here's a problem of counting tennis balls, right? And I give you the answer. And the next, you're like, hey, here's a problem of counting apples. Can you give me the answer? So the model will try to imitate what it seems before in the text prompt and give you its best guess. So this is like what's called a prompt engineering. This is how we interact with those models, those large language models. So at first try, you may think, okay, this model is probably not very good, right? Like it can't even count apples. What's a big deal? What's so crazy about those models? And that's what a lot of us thought a year ago. Those models are just not there. It's not human intelligence at all. But it's not the model's fault. Actually, we just don't know how to talk the right programming language, how to talk to those models. So instead, you can actually twist the way you interact with those models a little bit. Be like, not just giving me the answer right away of counting tennis balls, but also walk me through how you calculate those answers. So this is called chain of thoughts prompting, right? So instead of just asking the model, hey, give me the answer equal a number right away, can you carry out a calculation with words? It's almost like how you ask a question to a student, the student mumbles a little bit, and maybe even use a scratch pad and work out the answer. So that's the magical part about those large language model, is that it actually depends on how you interact and program them with your English words. You can actually guide them to solve more and more complex problems. And this is kind of opened up this new domain that's called prompt engineering, that everyone just like, if you go on Twitter, you'll see every day someone figure out a new way to talk to those models or teach those models, interact with them with plain English, not C++ or Python or whatever those like formal languages. And the chain of thought idea, prompting idea itself is actually very, very nice. I personally really love this. It's so simple and yet beautiful in the way that it decouples thinking from answering, right? Like the way we answer a question should be different from how we actually arrive to the answer. And in natural language, we get this for free of having this internal monologue. All right, so just a little bit, so far we talked about all those the black box, treat those models as black box, right? And you try to figure out what kind of alien language you need to talk to those black box to induce certain capability out of them. So how do those black box actually work? Well, turns out it's to me, it seems like the exact neural network architectures and learning algorithms, it doesn't really matter at this point. So what's really matters, think about them as with the way we train those models. So how do we actually train them? We train them is to predict the next word in the sentence it sees, right? So those models at every single time can see 2,000 words at a time. And the training objective becomes, given the previous 2,000 words, can you predict the next word in the sentence? And so in this example, for example, the input to the model is the nice cat sitting in front, right? And the next word in the ground truth data is off, right? So you're asking the model to predict the word off among all the possible words in its lexicon or in its dictionary. So it's very, very simple learning objective. You go through your entire training set and you ask the model to predict one word at a time over and over and over. So how many words has those models have seen? Like close to 1 trillion words, almost. So, and obviously, it's by definition in the name, large language models are very large. So how large are they? So this is actually a plot of, the amount of compute we spend with those models. 5 years ago, I gave a talk at Massey College. That's where I spend my grad student days at. And every time I talked about, hey, we're going to have machines and neural networks and AIs that scale that's just orders of magnitude larger than our current models, I always receive this counter argument of, but Moore's law is slowing down. We cannot jam more transistors into those models. We cannot make them even faster, right? But that's not true. What we're seeing here is you can imagine what I call the effective Moore's law. That is, we're building, yeah, sure, each CPUs are getting, it's harder and harder to jam more transistors into each CPUs, but now we're building larger clusters with more CPUs, and each of CPUs still getting faster, right? So that's what essentially sustained this effective Moore's law. And the models are not getting smaller in in the last 10 years, and they'll continue to follow this exponential trend of getting larger, right? So so when I first entered grad school, we were playing around with MNIST models at 2012 at the very bottom, and now the model size is almost like 10 orders of magnitude larger 10 years later. So with greater power, hopefully come with greater capabilities. So experimentally, turns out that's true, right? That's why everyone gets so excited about those models. They keep scaling up, right? It seems like scaling is it may not be the shortest path to reach certain capability, but certainly is the easiest if you have a lot of cash. So what are the capability can scale in brain? So it's actually pretty interesting. So there's various capabilities those models can have. They can solve math problems. They can follow the instruction to do translation, right? You can tell the model, hey, can you translate this sentence? Can you write me can you rephrase this sentence into a very viral tweet, right? Or even do 8-digit additions or all those things. So you'll see that some of those capabilities. So there are two curves here. X-axis is the number of flops we're spanning, right? And Y-axis is the capability. The higher, the better. Across a few of those tasks, more training flop with those models, the capability increases for some tasks, and the other ones doesn't quite increase as dramatically if you look at the black line. However, those are just directly asking the model to predict the answers. If you ask the model to actually spit out its own thinking process, i.e. the chain of thought, and then answer those questions, you will notice that the curves actually have this like hockey stick shape, right? So it's almost like, so this is an interesting part of those large language model is that their capabilities are kind of like, I guess back in the days, where else do we see hockey stick? Global warming, right? Where you see that as like it, so there are some certain capabilities that you just really hard to predict whether they're gonna emerge or not, right? So that's called like the emerging capability. Sometimes you'll see that on Twitter, and some of the papers read about it is like, if you train a small model and ask those questions, be like, hey, write a very viral tweet for me, they don't do quite well. And all of a sudden, you once you pass a inflection point of a certain model size, from GPT-2 to GPT-3, all of a sudden those models can do a lot better at those tasks. And chain of thought is one of those examples where the small models are not able to follow the think about step-by-step type of reasoning, right, to give you its own internal monologue of how to calculate the answers. But as the model get larger, there's this hockey stick takeoff that model often knows how to spit out its own internal monologue and help you to do the calculations and all those things, and also able to use the scratch pad and all those things to essentially help it as a tool to help itself to overcome its own essentially overcome to essentially help itself to solve harder and harder tasks. It's almost like you have this scratch paper and notepad, and you can just keep doing your drafts on those notepad. And scaling is not the only essentially advances in the last 2 years. Those components, so the jump between GPT-3 that we've been playing around with last summer to the ChatGPT now, this simulated quantum leap can be contributed to this technique called reinforcement learning from human feedbacks. That is, not only we ask the model to read the entire corpus of online text, but also we want the model to essentially produce outcomes that's valuable and useful for human. So in OpenAI, in order to make ChatGPT, what they will do is like they will ask the model to generate various different versions of text to the user, right? The internal user. And then the internal user will rank which of those generated results are more useful or less useful, or more valuable, less valuable. Then the OpenAI model will just generate more of those more valuable and useful results. And that's one of those techniques that's very crucial to distill the certain capabilities out of those models. So what's the intuition behind it? The way to think about it is you can think of like training on the entire internet text is almost like learning all different personas from the online data, right? But not all personas are very useful for solving certain tasks. What you really want to do is to distill out some of those useful personas for solving some of your downstream tasks. And how do you know which persona to distill out of your model? Well, that comes from user feedback, right? So human feedback depends on which kind of answer they prefer. All right, so another interesting fact or pop-up quiz here is that, so previously we talked about, well, if we have a lot of money to scale those models and we can collect a lot of user feedback, the model can do really well, right? Is there any task where if we just keep spending more money and make the model larger, the performance is actually going to decrease? Is that possible? So this is kind of like a quiz problem that proposed by this researcher called Ethan Perez from NYU. Now he's at Anthropic, asking the question of like, yeah, across a lot of the tasks we can measure the performance for, it seems like scaling is all you need, right? You make the model larger, the performance just goes up. Would there ever exist a task where as you make the model larger, the performance decreases? Turned out there is. And interestingly, some of my, so the two students I worked with, Sheldon and Daniel, they actually figure out one of those very, very neat observations that is, so they had this intuition of, as large language models get bigger and larger, they will and maybe make similar mistakes as human, right? They'll make similar logical fallacies as human, as they become more and more human-like. So what is an example of that? So consider this logical deduction statement, right? So if John has a pet, then John has a dog. Then knowing that John doesn't have a dog, so what should be and then I should be able to reach a conclusion, therefore John doesn't have a pet, right? So the question is this conclusion correct? Okay, this question is actually quite confusing for a lot of humans too, because it's you gotta figure out. So in philosophy, this is called the modus tollens problem. So that is, i.e., you're trying to essentially you given you given a statement P, and then statement P induces statement Q, and then if Q is not true, then P is not true, right? It's deductive reasoning, but a lot of time humans are not very good at this task, so it turned out that if you can test this, all those almost you can think with like logical puzzles to large language models, and something interesting happens too. Like the small models actually almost surely getting the answer correctly, but then as you get a model larger and larger, the models start to make mistakes, and very similar mistakes to human. And in fact, there's ongoing work so this work won I think the third prize of this inverse scaling law competition. And then there's actually a more general principle here that is, right? Like if we train on more human data, then those machines gonna be more and more human, right? The more human they become, very likely they're gonna make similar mistakes as we see on those online posts. So that's a pretty cute observation. So what are the so for example, if you are like economist, you would like this human have this time preference bias, right? Like hyperbolic discounting, right? Like and turned out that yes, if you make the model larger, yes, the model are gonna have more and more hyperbolic discounting than smaller models. And for a lot of you who are familiar with this book called Thinking Fast versus Thinking Slow, there's actually a beautiful analogy between thinking fast and thinking slow with directly predicting answers and predicting the chain of thoughts. Because thinking fast is like, give me the answer, 2 digits number right away, right? Quick. And thinking slow is when you actually have to, okay, wait a second, let me think about, so there's 2 apples here, 2 apples there, and then the 2 apples got dropped, and then how many apples there are, right? I have to run it through, and turned out you can actually activate 2 different modes of thinking in those large language models by prompting them properly. Interesting thing, I guess, moving on from I guess doing psychology and cognitive studies of those large language models, one of the interesting thing, looking into the future is, so this is a plot coming out of OpenAI paper back in 2 years ago on the scaling law for those large language models. Essentially, the problem they're trying to study back in the days is training those models clearly is very expensive, like tens of millions of dollars per model. So doing machine learning is almost training one of those models, almost launching a rocket, right, to a Apollo project. So back in the days, the stake is really low. In machine learning, the model is very small. We don't overthink too much about those hyperparameters. We just launch a bunch of experiments, do hyperparameter search. Now the stake is super high, and we only have one shot probably, right? Each model takes 3 months to train, tons of dollars. We don't want to waste any of the dollars. So we think for each of the hyperparameters, each of the knobs in those, models, we spend a lot of time thinking deeply about, how do we optimize them? So if you optimize all the models, all the knobs perfectly, and you say, well, how can I maximize the capability of this model, i.e. the y-axis as low as possible, and spending as little amount of compute as possible, right? So that's the optimization procedure that they were thinking about. And you can, you can build a very simple physics. It's almost like a prediction model on, how much compute you will need to reach certain capability. Back in the day, still like, hey, according to our model, we can trace those curves, and then we have two different models, and according to some prediction that we're pretty close to like reaching to the entropy of the natural text. What does that mean? That means like we're like there's be some inherent noise in the human text itself, and we're like orders of magnitude away from that, right? So this is where the GPT, like the intersection point is that point. If you're very speculative, that you can almost think those are the singularity points. Who knows, right? But the GPT-3 itself is around like I think according to this x-axis is like 2 or 3 10 to the power of 20 to the power of 3 petaflop days of compute. And although actually later on we found out the math of this OpenAI paper is wrong actually, so the slope of the red line curve is a bit steeper, but we're actually pretty close, right? So if we make our model 1,000 times larger, we're at this intersection point. And this is the point where we believe that we cannot make any more improvement to make the model stronger just by training on text data anymore.
Jimmy, pardon me. I'm going to just pause you here for a second.
Right.
And there's a number of questions that are piling into the Slack channel, and we'll come back to this. I want to just pause here as you're talking about the reaching this level of performance and then projecting into the future. I think ChatGPT was an instantiation of one of these models that it surprised people in its performance who were not, who weren't, who don't work in this domain and who weren't really paying attention to what was happening with these language models. But I think it even surprised people who were paying attention. And so for this, I'm going to first call on Jordi, and then go to Patrick Pilarski, and then Ken Nickerson. So Jordi, in your case, you'd been playing around with earlier versions of this from OpenAI. And then when this came out, you were surprised by its performance. Can you just describe what parts that you found surprising?
The question for me?
No, this is for Jordi.
Okay.
Thanks, Ajay, and hey, Graham. Haven't seen you around for a while. Hope things are well.
Nice to see you.
Yeah, likewise. Okay, so I'm gonna have to be a little bit curmudgeonly here, and I'm sorry, I'm going to have to channel a little bit of Noam Chomsky and Gary Marcus maybe, but these are not language models. So there's an unfortunate naming convention that's being established, but they don't model language. I think it's important for everybody listening here who's not a technical person to understand that what they do is very much like and maybe identical to what you could think of as auto-completion, where you have a probabilistic, basically random number generator that just rolls forward a set of text into more text. And the reason that's important is that many people, including myself, don't believe that's the way that people generate language, and that statistically analyzing a bunch of text tells you something, but it kind of completely misses the point if you're interested in how we do language and what language is for. So if you want any more on this, I won't go on about this at any more length, but if you're interested in the other side of this, I'd read some of Jan LeCun's descriptions of how he's viewing the emergence of these models. I think he's got a very sober and balanced, even though he looks like he's playing the other side, but I think he's actually quite balanced about how he feels about these things. So getting back to the question about the surprising nature of these. So yes, I have been a fan of these statistical token prediction models for some time, all the way back to the char RNN days and even before. Graham and others who have been in this game for a long time will recall that these things have a long and storied history of these auto-regressive things where you're predicting stuff. It's a very old idea that has always been interesting. In some ways, it was kind of predictable that people were going to try to make them.
Ken, did Jordy just cut out for you? Yes. Okay, I think his internet froze. So there'll be something, Jordy is about to say something interesting, but we're going to miss it. We'll come back to Jordy. Let me go to Patrick Pilarski, and then Ken Nickerson. We'll come back to Jordy. Hopefully he'll be back by then. Patrick, anything on your side?
Yeah, thanks, Ajay. I think, like, I should say up front that I have great respect for systems that create associations over both space and time. And so the machines we're talking about do a great job of this. This is something that in fact is commendable. The bits of our deep brain structures that we appeal to navigate through the world around us do exactly these same kind of things. They try to build associations across different modalities and across time. So I have great respect for all that. I think I had a comment earlier up in the chat where I really said that I felt that though the systems we're discussing today are fragments that are frozen in time. And I think that maybe I'll expand on that and say that it's no surprise maybe me saying this in that a lot of us, Rich Sutton and I, and Mike Bowling, others have come out publicly and said that we believe that continual learning is really important. That systems that continually learn through a stream of experience where there's no specialness about a moment in time in terms of training and testing, where, oh, you distill data at one point in time and then you go forward in the world and then use that. I think that I do feel that the things we're discussing today and that Jimmy's really painted an amazing picture of are snapshots in time, and there's a limitation to that we should all address. They do miraculous things in some cases. In some cases, they make up quite a bit of bullshit. But either way, I think that the kinds of associations, and Jordy was speaking this as well, like they are in fact doing these kind of spectacular rollouts, and those are based though on these learned associations. So we should respect that. Think that's great, but these are artifacts that are frozen in time, and they aren't continually learning systems that build from experience. I think it's important to contemplate what it means for a system to actually build from a continuing stream of experience, as opposed to a snapshot of a past stream of experience, be it the full weight of human knowledge.
Thanks very much, Patrick. Ken Nickerson, anything that you'd like to add on this one?
Sorry, I'm trying to get this darn speaker to work. Yeah, look, I'm a huge fan of everything, and I love playing around DALL-E and ChatGPT. But Feynman had a great line. Richard Feynman, he said, "People are easy to fool, and the easiest person to fool is yourself." And we love suspension of disbelief. For a child up to the age of 6, every Disney movie is a documentary. And we inject ourselves into it, and the question is the results from LLMs and ChatGPT human-like, or in our minds do we mold it into, like when we read a cartoon or watch a movie, we mold it into being more human-like? I view all of this as a cul-de-sac of AI. We've had other cul-de-sacs back in the 80s with expert systems. We thought we found the model of the human mind. Without associative memory in particular, I just don't think we're on the right path. Well, this may be useful. We may get rid of, millions of call center jobs and other things, but it has serious trust issues. It has serious temporal issues. And the training issues, I'll shut up after this, but the training issues are interesting to me, and the way I think about the training issues, when I was, like everyone here, 3 or 4 years old, I touched the stove once while it was on. I did not have to touch it with the rest of my fingers, toes, and tongue to realize that's a bad idea. And when I look at the way generative AI is asymmetrically developed through weekly or monthly, depending on what your budget is, it's just, to me, a cargo cult-like model of where we're going, and we're going to have to eventually take it all, throw it all out, and start over.
Okay, Ken, thank you. As you know, at Creative Destruction Lab, we're focused on the mission of Creative Destruction Lab is to enhance the commercialization of science for the betterment of humankind. And we put a great emphasis on the people who actually turn these innovations in all kinds of domains, life sciences, computer science, engineering, and so on, into products and services that benefit society. And so we're very lucky to have somebody who's really leaned in on this and is doing just that. And so, despite the various limitations that have been raised in these preceding comments of what these models can do, obviously they can also do remarkable things. And so Aidan Gomez is building a company that is doing just that. So let me ask Graham if he would introduce our next guest, Aidan, who has really been a pioneer in this field.
Sure. So Aidan Gomez, he's co-founder and CEO at Cohere, Canada's most recognized and advanced provider of LLMs. And he's often referenced as the co-author of the foundational paper, Attention is All You Need, which introduced the world to transformers. And he's studied, like Jimmy, like myself, under Jeff Hinton, and Aidan has collaborated with Jeff Dean, the famous Jeff Dean. He holds a Bachelor of Science in Computer Science from the University of Toronto, and he's pursuing a doctorate right now at University of Oxford. And not too long ago, he was on the stage at the Elevate Festival being interviewed by Stephen Marsh, a recent guest at this reading group. So it's an interesting way, I thought, to connect the dots. And Cohere is creating an interface to LLMs intended to be accessible to any developer. And that's why I thought he'd be a great invitee for tonight.
Excellent. Thanks, Graham. Aidan, welcome.
Thank you. Thank you. Great to be here.
So first off, congratulations on the success of Cohere so far. And let me just begin by inviting you to react to, if there's anything you'd like to react to of comments that have been made, and then we'll turn to some of the very interesting work that you're doing at Cohere.
Yeah, I'd love to. First off, Jimmy, thanks for such a excellent intro to LLMs and how impressive they can be and the strides that we're making. It's not often that you're in a room with some vocal critics of LLMs. I think there's a lot of hype around them, and so it's refreshing to hear some of those criticisms. Just to react, like I think what I heard was initially, this isn't how humans do language modeling. I then also heard that they're trapped in time. And so recency and continual learning is a problem. On the first point around whether humans learn this way, I'm not a neuroscientist or a linguist, and I don't claim to know too much about that, but I think it doesn't matter. I think what matters is that the models actually perform and that they're capable of doing useful, valuable things for the world. Whether it maps onto the way that we humans learn or, we humans approach the problem of modeling language, I'm fairly disinterested in that. So long as it works, that's what is important. On the continual learning piece, I think that, Cohere is one of many building these models, and that is a problem that needs to be tackled. As the world changes, if a model stays stagnant, it becomes less and less relevant over time. And so efforts need to be made to bring them up to date, to give them access to, the latest knowledge and information. I think there's really promising directions, in particular, augmenting these large language models with access to a database that's kept up to date, at the millisecond level, something like, for instance, a search engine, right? As the world changes, the search engine is always up to date. It's just a index over the internet. And so if you give these models the ability to use a search engine, to be able to query it, to find information about the world, if you create new knowledge bases that it can make reference to, you give them the ability to be as recent as the last millisecond. So both of these I don't view as fundamental blockers to utility. I think comparisons to the sort of like autocomplete or the stuff like the last generation of these sorts of models, I don't think they're very fair. I think that something very extraordinary happened in the past half decade. The types of capabilities that we're seeing, their behavior and how they map onto humans. It's important for us to remember how recently it was that we were having trouble getting these models to spell correctly. If you look at pace of progress, now they're doing hyper complex things like writing entire essays that are indistinguishable from what a human might write. I think the pace of progress is extraordinary and it's only accelerating. So yeah, I'm obviously biased and very bullish on the space, but I don't see fundamental barriers for us continuing to make breakthroughs and continuing to cut closer to human level performance on tasks and problems that, it would have been a dream to come close to humans only like 2-3 years ago. So yeah, I think that's a fantastic thing for the world. And I think poo-pooing progress and pointing at its flaws and trying to come up with a list of problems is actually super productive, because we need to know what to work on. We need to know what barriers to overcome. So I'd urge you to continue to criticize the technology.
Aidan, thank you. Let me invite Michael Kuhlman, who has a question about private data sets. And there's quite a few entrepreneurs on this call, as well as business leaders of large corporations. And I suspect, Aidan, many will be interested to follow up with you just in terms of how they can sign up for your service. So many people have been reaching out to me in preparation for this session, just trying to navigate where can they get access as corporations to begin experimenting with these. But Michael, why don't you begin with your question on access to data?
Yeah, thanks, Ajay. I guess we've been trained, in the definition, large language models, we've got the word large. So presumably these things they work well, the more data that we fed them. I guess my question is, how applicable is this to closed data sets that are much smaller? And is there sort of a minimum level of data you need to feed a system like this for it to have valuable output? And so, yeah, in my mind, it's enterprise applications that I'm thinking of, where people have collected, gobs of proprietary information that they want to unlock. And, the best way we have today is people using, business objects and, dashboards with pie charts to do that. Whereas, a chat interface clearly could, using natural language, is accessible to everyone. So how realistic is that? And is that even possible?
Yeah, so Jimmy was describing like training the initial big models, like these large language models. That requires like he mentioned, trillions of words. We scrape billions of web pages to do that. But the whole point of doing that is so that the next phase, the order of magnitude of data is like dramatically less. So there's actually a hierarchy of these models. And that first one, the one that Jimmy described initially, it requires tons of data, but the one that he described after that, the one that's tuned by RLHF or reinforcement learning from human preferences, it requires something like 30,000 examples. That's it, right? Like, so you go from billions of web pages down to 30,000 examples to have a huge step up in performance. Going beyond that, there's a layer that's built on top of that. So at Cohere, we call those RLHF models command models. But as you've probably interacted with ChatGPT, chat models or dialogue models are the next step up. And again, it requires tiny, like minuscule amounts of data to tune the model into that modality. And suddenly they're able to converse and have really compelling dialogues. So That's just to say that, yeah, the big model does require tons and tons and tons of data. But as you start to actually use it and deploy it, and you start getting more specific on your application, I don't want you to be a model of the web. I just want you to be a chatbot. You only need a tiny amount of data. The data privacy piece, I think, is really interesting. That's a huge barrier to adoption. Like, no enterprise is going to use this if OpenAI is training their next model on your private industry secrets or, like customer data. And we've actually seen that start to happen. So folks at Amazon, internal Amazon employees, they were entering in stuff about internal Amazon secrets into ChatGPT. And the next version that got released, it knew those secrets. And so Amazon HeadCorp was just like, their GC came and just cut it off. No one can use this. If you're on our internet, don't touch this. That same thing has been replicated across a bunch of different corporations because it's so sensitive, and you're just leaking it directly to Microsoft. For Cohere, we're really billing ourselves as like the enterprise partner for LLMs. So private deployments on-prem within VPCs. None of your data gets used to train anyone else's model. It's all yours. So hopefully, like, I do view that as like a core blocker to adoption for enterprise. But hopefully Cohere and others will start to offer that as a feature, because right now on OpenAI, you're just leaking data into the void.
Thanks, Aidan. Just on the enterprise question, I see Carrie Covent here. Carrie is one of the largest retailers in the country at Canadian Tire. Carrie, as you think about bringing these types of language models into your business, what are your primary frictions or the questions that you're trying to navigate in order to figure out where to start?
So, can you hear me okay?
Yep. Yes, we can.
Okay. I mean, I think my question was similar to Michael's. And in terms of data, one of the things that we're thinking about is how can you combine the training data from the internet with data specifically in a closed environment to actually produce something that would be of value to the organization? And is that possible?
Yeah, I'm really excited about transforming customer support, but that can't happen if you have an agent, like a synthetic agent that's not speaking in the voice of the brand or isn't familiar with the brand's product offerings or services. So for us, definitely being able to fine tune these models on a specific voice, a specific tone, being able to give them access to, a product catalog that it can make reference to and query and look up items, as well as giving it access to that particular user's buying history. So it knows what that user likes and can recommend similar products. All of that is very much possible and is roadmapped.
Okay. So Ajay, that's kind of where we're looking to go. So.
Okay, great. Let me. I'm going to go to Janice Stein, and then I think I saw a question come up from Kiran Sohi. Actually, let me go to Kiran first, and then to Janice. And Kiran, this is your question about the automated errors from training and testing.
Yes. So I guess what I'm trying to figure out is, and I haven't done LLMs at all, just very personally, very basic learning and machine learning stuff, right? And very brief knowledge of NLP models. But one of the things I've always noticed, and this has to do more with, the process of developing these models, is that you do the training, you do the testing, and then you understand how good this model is, whether it's like 70% to whatever, 90%, whatever it is. And then you leave all that information behind and put the code in production that outputs that data somewhere between 70 to 90% accurate. And I was working with some of the machine learning or our data science team to see if we can actually build some kind of confidence interval on what we're trying to optimize or minimize. And that's where my knowledge goes only as far as machine learning, as I said. But in the NLP world, obviously truthfulness and these, and other rates that are automated, like, is there a way to bring these things forward so that every time there's an output, is there an indicator as part of that output that says, look, this is 100% wrong. Basically, it's pure hallucination. Versus, this is 70% right, so you better check it, or this is 90% right, so you might get away with it if you actually put it out in the public. So I guess in the cases where that's very important, in use cases where that's important, is it possible to do that?
Yeah. We're hearing this a lot now, like the notion of expressing confidence alongside some response, so that can be a variable in your decision to accept a large language model's output or not. So there are some naive things you can do. For instance, you can just use the likelihoods, and you can say if this model is saying that its output is extremely likely, that must mean it's very confident. There are issues with that. And so like the current answer is that that's something that's still research. There are techniques and research that I'm sure Jimmy and Graham and others can attest to. Like the field of uncertainty quantification has been going on for a really long time now, and there are good methods to get pretty good measures of uncertainty from any neural network. And so it seems like this is something that industry needs in order to adopt these models. They need to be able to trust those outputs. They need the models to be able to express some degree of certainty versus uncertainty. So I'm hearing that a lot. The good news is, there are methods that exist. The naive ones aren't so great. There are probably some more computationally expensive ones that we could pursue and expose through Cohere that are a bit better. But yeah, that's kind of the state of the art there.
Okay, so that's a PhD for someone. Definitely. Thanks. Thank you.
Thanks, Aiden. Just before we go to Janice, and for Janice, of course, feel free to go wherever you want to take your question. But Aiden, where are you so far experiencing the greatest pull on the commercial side? In other words, there's been almost like an infinite number of ideas since ChatGPT came out of what you could use these for. And of course, you need to prioritize inside the business. So where are you sensing the greatest sort of commercial opportunities for these particular kind of models?
Yeah, so I think the conversation has changed so dramatically. Like it's, for me, I don't know how it feels for everyone else, but for me, it feels so insane that it was like 2 months ago that ChatGPT came out. 2 months and 1 day ago, when I was having conversations with executives inside, large enterprises, the conversation was me explaining to them, here's what an LLM is, here's what you might be able to do with it, here's how you can tune it. Now it's completely flipped. They've all had like first-party experience actually interacting with LLMs, and they come to me being like, listen, I have this amazing idea. I'm going to plug LLMs over here. And so it's been a really exciting change of script or pace. I think in terms of the areas that are highest urgency, or what we're seeing at Cohere, so the chat nature of ChatGPT has really oriented people's thinking. It seems like dialogue systems are really where people are excited right now. Customer support is a huge one. I think another huge one is actually being able to interface with your organization's knowledge through conversation. Like imagine there was someone at your organization who had read every single document, who had listened in on every single, call with your customers internally, etc. And you could just talk to them and ask them questions about the organization and its operations over the past decade. We're very close to something that's capable of that. It's not actually that far away. Like we have these chat systems that are really compelling. We have large language models which can query databases, which might consist of all of your company's internal documents, your emails, your chats, your Slack, whatever. And so I think being able to have, let me just choose an organization at random here, Nike, like chat Nike. And it's an agent that has access to all of Nike's internal documents, all of their products, their call transcripts, their CRM, whatever. And so as a resource for their employees to go to and ask questions and surface knowledge and information, I think it's completely transformational. So I think as an aid to knowledge workers, it's going to be extremely impactful.
Thanks, Aidan. Janice, I'll turn to you, and then Mark Torrance.
Thanks so much, Jay. And wow, Aidan, listening to you talk. My question actually built on something that Jimmy started and Ken really began to develop. I was absolutely intrigued, Jimmy, when you said that as the models got larger, they became more human-like, but they actually began to replicate human fallacies. Now that's counterintuitive. That's not what you hear when we talk about larger and larger models at scale. And so here's my big question to you as we're at this point, which I think most of us would agree is transformational. Is the hope here that LLMs will do, in a sense, what Ajay was talking about earlier, become more human-like? Or is it, in fact, that LLMs will develop the capability to recognize deeply embedded logical fallacies and give, and in effect, produce knowledge that eliminates those fallacies? And I know that's an issue that Ajay is interested in.
Janice, thank you. Let me let Jimmy have the first go at it, and then Aidan can come in.
Yeah, I guess to me, that's, I guess on the research side, we're asking ourselves, so now you see this like inverse scaling,
yeah,
model size. Do we ever see a U-turn? And it's I personally, I won't bet my money on just training on internet text. So in the sense that the intuition here is the following: training on all the internet text is essentially learning, the average Twitter user, right?
Bias.
That's right. And then garbage in, garbage out. That's the machine learning system.
Yeah.
And even for those logical fallacies, also that's really hard for human. Only maybe like a few of us who the people in this room is probably can do better than average on those problems. So now if you can somehow collect their chain of thoughts, right, on analyzing those problems, to me that seems like the probably the shortest path to be able to fix them. So yeah, so now it's really just about, we don't just want the average Joe intelligence, right? We want like a business executive who can make cool-headed decisions and make logical deductions that be able to make a case, make a business plan that actually sound and logical. Majority of our training data are not that sort, so that's the current bottleneck.
I'll just say, Ajay, before you throw to Aidan, there's a whole reading group session based on Jimmy's answer right there.
Yes, there is. And I should just say, reminding everybody of our DIE policy, that we don't discriminate against the average Joe. Average Joes are just as welcome here as everybody else. Okay, Aiden, anything you'd like to add on this point about scaling?
Yeah, I think I think Jimmy's 100% correct. We want to model the very pinnacle of humanity. I think Janice's question touches on, well, what happens if we want to go beyond the pinnacle of humanity? And that's a really, really fascinating one. How do you do that, right? Like Jimmy points out that the web, you just model the web naively, you're going to probably end up with the average Joe, which is amazing and super impressive. And, you know, no one would be dismissing that 5 years ago in machine learning for sure. But there is a question now around how do we get superhuman capabilities on a wide range of tasks. I mean, I don't know the objective answer to that. I think one way that we've seen that happen is the folks at DeepMind with AlphaGo, and in particular, I believe it was called AlphaZero. They started off by modeling human players, and they eventually reached the point where they eclipsed the best player in the world. But they didn't stop there. They then got this agent to start playing against itself and self-improve. It had to now beat itself, and it just kept getting better and better. And it just eclipsed anything we thought would be possible in the game of Go. You can imagine something similar being set up, for instance, in ChatGPT models. What happens if you don't have a user on one side of ChatGPT, but you actually just have another model, and the model is challenging another model to accomplish some task for it, and they're consistently having to self-improve. You can run that a lot faster than you can with users, because humans take a while to read the screen, type in a response. Humans are massively parallel. There's 8 billion of us. But when you just put this all on silicon and you let these models talk to each other back and forth, you know, at full speed, at the speed of light, what pops out the other side of that self-iterative process? I think it's a really fascinating question.
Thank you, Aiden. Just the last comment or question from Mark. Mark, over to you, Mark Torrance.
Thanks. Wow, what a fascinating conversation. And a lot of the topics that we talked about in Slack have come up in the live conversation, so I really appreciate that. I just want to say kudos to having the Slack going, because I think it really increases the bandwidth of a massive conversation like the one we're having today. And I hope that that conversation continues in the Slack. I think that the one issue we haven't talked as much about yet in the live conversation is ethics, and whether there are questions about, like, should this be released to the public, and are students abusing their educational process by using it to write essays and that sort of thing. So I'm not really sure who the right person to address that to is. Maybe Ajay, you could recommend a responder or two for that topic.
Sure. I think let me see if
Ajay?
yeah, go ahead.
Gus Scorberg's here.
Oh, that's a great idea.
Professor of ethics.
Yeah. So Gus, why don't we turn to you, and then Graham, just being the role that you play in academe and your center, I think you'll also have a comment on this. But Gus, why don't we go to you first?
Yeah, thanks for the thanks for the prompt. For those that don't know me, I'm Gus. I'm the academic co-director alongside Graham of our AI Ethics Center at the University of Guelph. And so obviously these are big questions that are front and center for us. And I guess in my head, I try to divide it up into two kinds of spaces, right? And so there's questions we can ask about, like, how do we ensure that these models aren't, disclosing private information, right? And there's just sort of technical questions about limiting the bias in the output. And so the kinds of questions that, like, engineers are going to be really well suited to answer. And then there's these sort of bigger, like, political questions, right? Which is asking, what does it mean that there's only a handful of organizations that have the compute power to even run these models? And like, what does that mean for our society? And like to me, those questions aren't ones that are like machine learning questions, right? They're political questions. And I think it's important to distinguish between those two. And so obviously what's so great about this group is, we've got the political scientists, and Janice, we've got the sort of machine learning people. But I think keeping those two questions separate is a good way to sort of guide future discussions about those topics. Yeah.
Gus, thank you. I'll since you referenced Janice, I'll go to Janice. But first, I'll just realize Jillian is here, who's thought deeply about this, and obviously you come from a legal background. So Jillian, I know you could give a 3-hour seminar on this topic. So why don't you just pick whatever you think is sort of most interesting for this group?
Yeah, I think the thing to think here is that, you need to be thinking about what's going to be built on top of this, both in terms of the fine tuning systems that will be built on top. Like I commented, I've seen some amazing legal stuff that's being built on top, as well as the regulatory apparatus. We actually just, we think again of the legal example. We have lots of rules. I think we have too many of the wrong kind of rules around who can give legal advice in what framework. And I think we need to be thinking about what those regulatory regimes. Same thing with education and banking, and we just don't want to think about ChatGPT in sort of raw form, or these models in raw form. So I think these are regulation questions and less ethics questions, actually.
Jillian, if you could pick one innovation that you've seen, or one even innovative idea that you've seen in terms of regulatory approach to these large language models, is there anything that stands out to you as being particularly interesting or compelling?
I don't know that I've seen anything yet, but I think the piece. Well, let me put this differently. Actually, again, in the legal domain. So thinking about the fact that the raw system is going to, make stuff up. Okay, you build a system on top that has to verify and show where in the case law does it say this. So you could imagine that as a regulatory structure that could also come through, and a test that we would put it through before it was authorized to provide legal advice. So I think those are this is what I think this is the regulatory challenge we need to be really focused on right now with the language models is what systems can we put in place to assess reliability so that people can trust what's coming out.
Thanks, Jillian. Janice, anything you'd like to add on the ethics question from Mark?
So much the ethics part. It's not so much the ethics part of Mark's question, but because you also asked about education, and probably nothing's gotten greater attention in the last 2 months and 1 day than what this is going to do to education from primary school right through to universities. There's a lot of apprehension. I actually feel I feel exactly the contrary, that this will be a phenomenal tool. It hopefully is going to shake up faculty as well as students, because we're going to have to rethink how we define expectations for students and how we can enable students to use these kinds of tools, but then build, as Jillian said, in a different way, Jillian, just build on top. How do we help students build on top of that and use this generative AI to advantage so that they become both skeptical but build on the incredible efficiencies of this kind of tool that I think will only get better and better. So I think it's a great moment to be in education, I think, Mark.
Janice, thank you. Carol, if you can bring up the slide, and Aiden and Jimmy, just I'll ask you to comment on one last thing here. Think of this as lightning round, so short, concise response on the future, and in particular, I want to invoke the idea of emergence. So, as these models get bigger, they're trained on more data. There'll be, to some extent, some kind of like linear improvement that we can imagine that they get better in ways that people would kind of expect after they've experimented with the models that exist today. But if something were to emerge that would be surprising in terms of their capability, that's not just a linear extrapolation of what we've seen so far, what do you think that emergent thing would be? Jimmy, I'll ask you first and then go to Aiden.
I'm often wondering about that question as well, and I'm ready to be surprised.
Is there anything that you would speculate in terms of what will be the thing that will, the next thing that will surprise you and surprise people in the field of its capability?
Well, if I can anticipate it, I wouldn't be surprised.
Okay, fair enough. Maybe I should have said what might surprise others. But Aiden, let me turn to you and see if you have anything that you'd like to suggest on this one.
Yeah. No, it's such a tough question because we're in this space where you'll say something and within 6 months it'll be solved. And so it's really hard to look forward. There were all these things that I thought were the exclusive domain of humans, which now language models do easily, that it's so hard to look out in the future. I mean, one thing that's really cool that I think is coming this year is the ability to use tools. So we've built tons of tools for ourselves, apps, websites, the computer. I think one of the next big things for large language models is that they won't be stuck in a box anymore. At the moment, sorry, this was supposed to be a lightning response. At the moment, they can just stream text back at you, right? That's the only thing they can do. That's how they affect change in the world, is just by talking to you. Well, what happens when we give it access to an internet browser? You can ask it to do something and it can, surf the web and click stuff, and literally anything that someone can do in front of a computer on a web browser, the model can now do. It's out there, it's affecting change. I mean, it would shock me if that came within the next 6 months, but I feel like it's coming in the next 12. It's getting really, really difficult to carve out something and say, no, this is exclusively human. There's no way language models can do this. I think that's an extraordinary reality that we exist in.
It's too bad that so Jordy and Suzanne both were in the same building and lost their internet connection. But what I would have asked them to talk about is right after ChatGPT came out, they started running experiments with using the language models to do task planning for robots. And what they found was it was shockingly good. And that meant that it was taking the capability of these language models that so far most people seem to be using just as creating text on a screen. And they were now using it to manipulate things in the physical world. In other words, you'd give the robot a basic text prompt, just speaking to it like unpack the boxes and put the shoes on the shelf. And then the language model would convert that prompt into a very detailed series of tasks using the verbs that the robot understands, like pick up, grasp, move, drop. And so it convert this into this list of tasks and all of a sudden enable a person to communicate with a robot and the robot to be able to then perform an incredibly wide variety of things. So anyhow, I will ask them to comment on this next week. And just to give people a preamble, we're doing 3 weeks on language models. So today, we would have what I would view as 2 optimists, Jimmy and Aiden. Jimmy, a prolific researcher in this domain, and Aiden, building this incredible Canadian company and being a researcher himself. Next week, a more critical view, Ted Chiang, who we're reading both a fiction piece by Ted and also a nonfiction piece that he published a few days ago in the New Yorker. He takes a quite a bit more critical view of the capabilities of language models and their future, at least like on their current trajectory. And then our final week, we go back to the optimists, and a psychologist, Mikhail Kaczynski, who's taken a view that there's an emergence of a theory of mind that has resulted from the development and growth of these models. And then Corey, who's created this dramatron for the creation of theater scripts and screenplays. And he's going to get under the hood and explain how this works. So that's our 3 weeks focused on, I'm hoping that by the end we get through these 3, we've kind of traversed a fair number of the for non-practitioners, some of the key areas in this domain. I want to close by thanking Jimmy. Thank you very much. I can imagine when a domain like this explodes, I'm sure your inbox is filled with an infinite number of requests to come and explain to people what's going on. So really appreciate you taking the time. Aiden, same. Thank you very much, both of you, for joining us.
Thank you so much. Such a pleasure.
We ask everybody in the Slack channel, there's a survey. If you don't mind, please just take a minute to fill it out with any thoughts on the session this evening. And then we're also going to break into small groups for 15 minutes for those who want to stick around and just have small group discussions. Jimmy and Aiden, you're welcome to stay, but don't feel obliged. You'd just be randomly assigned to one of the small groups if you stay. But like I say, don't feel obliged to stay. And thank you everyone for joining, especially the people who came for the first time tonight. Thank you for joining us, and we will see you next week. Next week, we're back to Tuesdays. Tonight's Wednesday because of Valentine's yesterday, but after this, we're back to Tuesdays. See you next week.
I did my best to notice when the call came down the line.